everybody, and welcome back to Biology with Gracie. Welcome back to another video. Today I'm going to be starting a sort of mini series on statistical tests for A Level Biology. If you're studying A Level Geography, this is also relevant as you do need to know about a few statistical tests. I feel like this can seem to be a really tricky math skill in A-level biology, when actually they are relatively simple. You're given the formulas for these statistical tests, and I think it's only tricky when you need to work out which one to use. So in this video and in this mini series, I'm going to try and to explain how to use these formulas, use these tests, and work out when they're needed. Today in this video I'm going to be talking about the chi-squared test. So this test is used to test the significance of the difference between observed and expected results. So observed being the results that you get once you've done your experiment, and the expected being the results that you predict. So for lots of statistical tests, you need to know about the null hypothesis. So you may have heard of hypothesis, which is basically a prediction you make. And the null hypothesis is an opposite to this. So a null hypothesis states that there's no significant difference between observed and expected results. So this statement is slightly changed to adjust to different scenarios, different experiments, and we will be going through an example where I will state a null hypothesis. So if the chi-squared test shows that the observed and expected results are significantly different, then the null hypothesis is rejected. So for this kind of statistical test, we can't prove that it's true, or we can't accept it. We can only fail to reject it. So unfortunately the evidence doesn't give a reason to think the null hypothesis is wrong, but it can give some evidence to reject it. So we're going to go through how the chi-squared test is carried out and how we can get to this conclusion. So for chi-squared, there is a specific formula and it looks like this. Now, when you look at that, you may think that it looks very confusing or difficult, but it is actually fairly simple. So the sort of x symbol at the front, the x squared, is chi-squared. So that symbol represents chi-squared. So chi-squared equals, then we have that sort of funny little zigzaggy e, that just means sum of. So chi-squared equals sum of, and then O represents the observed results and E represents the expected results. So we have chi-squared equals the sum of observed minus expected results squared divided by the expected result. And don't worry, you'll be given this formula in the exam if it is necessary to be used. So you don't need to remember this, but it's definitely important to know how to use it. So we're going to go through an example here. So just as an introduction, we have our theory. So the theory is that the height of pea plants is controlled by a single gene with two alleles. So this is known as monohybrid inheritance. So we have our dominant allele, which is a big T, which is for tall, and then we have our recessive allele, a little t, which is for small or dwarf. So the expected results for monohybrid inheritance is a 3:1 phenotypic ratio. So remember back to genetics that phenotype means this characteristic expressed or observed. So for example, phenotype could be eye colour, blue or brown eye colour, or your hair colour, or height in this case. So our phenotype for this example is height. So there's a 3:1 ratio. So it should be a 3:1 ratio of tall to small in the offspring. So in monohybrid inheritance, we cross two heterozygous parents. So heterozygous purely means that the organism carries two different alleles. So our heterozygous parents in this example are going to have the alleles big T, little t. So if we were to draw out our genetic cross, this is what it would look like. So we have our parents, big T, little t in the darker pink, crossing together to make our four offspring. And as you can see, these three here have big T's in them. And because big T is dominant, this means that this characteristic of being tall is going to be expressed. Whereas for this one here with little t, because there's no dominant allele, this plant is going to be small. So as you can see, we've got 3 here, 1, 2, 3. So there's our 3, and then 1. So our 3-to-1 ratio of offspring. So then for our observed results, the experiment is carried out. So in this case, our experiment is crossing 2 heterozygote plant parents, and then the number of tall and small plants, so the number of tall and small offspring, is counted. So therefore, our null hypothesis is, of course, that there's no significant difference between observed and expected results. So when we cross 2 heterozygote parents, we expect, due to monohybrid inheritance, so that there's going to be a 3-to-1 phenotypic ratio of tall to small offspring. We then have our results. So if the chi-squared test shows that the observed and expected results are not significantly different, then we are unable to reject the null hypothesis. So in case of our example, if our observed and expected results are not significantly different, so if we do find a similar 3-to-1 ratio of phenotypic tall to small offspring, and then the data we have supports the theory that the height in this plant is controlled by monohybrid inheritance. So now we're just going to go through an example of a calculation we would make. So we've got our heterozygous parents, so big T, little t, and they are crossed. And in this experiment, 60 offspring are produced. So first, we need to calculate the number of offspring we expect. So we have our phenotypes, tall plants and small plants. Our expected ratio is 3 tall plants to 1 small plant. So our expected result is therefore 45 for tall plants and 15 for small plants. So the way that we calculate this is 60, which is our total offspring produced, divided by 4, which is our ratio total. So the expected ratios of 3 and 1 added together are 4. And then we times by 3, which is the expected ratio for tall plants, and this is how we get 45. So then for small plants it's exactly the same, except that we use 1 for the expected ratio for small plants. So 60, which is the total, divided by 4, the ratio total, times by 1, the expected ratio for small plants, and this is how we get 15. So we then need to record the number of offspring we observe with each phenotype in the experiment. So we've got our table again, we've got our expected ratios, expected results, and now we have our observed results. So during the experiment, tall plants that were produced which had this phenotype was 42, and plants that were produced which was small was 18. We then use our expected and observed results to calculate our chi-squared. So we can do this in steps, as I've done here. So for A, we need to do our observed result, take away our expected result. So if we have a look at our tall plants first, so we have our observed result, which was 42 tall plants, and our expected, which was 45 tall plants. So then we need to do 42, take away 45, which gives us -3. If we then have a look at small plants, so our observed result is 18 and our expected result is 15. So 18 take away 15 is 3. We then need to square these results. So -3 squared is 9. Remember, a negative times a negative is a positive. So we have 9 here. And then 3 squared is 9 as well. So then finally we need to divide these values by our expected. So we need to do 9 divided by 45 for our tall plants, which is 0.2. So 9, our value here, divided by our expected result of 45. And then for our small plants, we need to do 9 divided by 15, which is our expected result, and we get 0.6. We then need to calculate the sum of these values. So remember that this weird little zigzaggy E means sum of. So we have our table here. So we need to do 0.2, which is for our tall plants, remember, and then 0.6, which was for our small plants, add them together and we get 0.8 here. So finally, we need to find out whether there is a significant difference between our expected and observed results. So we do this by comparing our chi-squared value to a critical value. So a critical value is basically the value of chi-squared that corresponds to a 0.05% level of probability that the difference between our observed and expected results is due to chance. So that's a little bit wordy, but basically as biologists we use 0.05 as our level of probability. So if you're given a table, this is the column that you need to look at. So basically we're going to compare our chi-squared value that we've calculated to another value. So if our chi-squared value is greater or equal to the critical value, this means there is a significant difference between our observed and expected results, and we can reject the null hypothesis. However, if the chi-squared value is less than the critical value, this means there's no significant difference between our observed and expected results, and so we cannot reject the null hypothesis. So therefore, the theory that we have is supported. So in your exam, you may be given a critical value or you may be asked to work it out from a table. And so we're going to go over this on the next slide. So using a chi-squared table, the first thing we need to do is calculate the degrees of freedom. So all we have to do is do the number of classes, or in this case phenotypes, minus 1. So we have our degrees of freedom here and our number of classes. So for our example, we have 2 classes or 2 phenotypes, which is tall and short. So we need to do 2 take away 1, which equals 1. So our degree of freedom is 1. We then need to find our critical value in the table. So the critical value, remember, we need to find is corresponding to a 0.05 probability at our relevant degree of freedom. So remember that biologists use a probability level of 0.05. So look in this column in your exam. So remember this value. So we have the table that will be given here. And remember that our degree of freedom is 1, and we need to look at this at a 0.05 probability. So we've got our degree of freedom, so 1, so we're going to be looking across this top row here, and then we have probability of 0.05. So therefore our critical value is 3.84. So we then need to compare our chi-squared value to the critical value. So if you remember back to our chi-squared value, which was 0.8, so it was 0.2 for our tall plants plus 0.6 for our small plants, which gave us a chi-squared value of 0.8. So 0.8 is smaller than our critical value of 3.84. So therefore the difference between our observed and expected values is not significant. So this means that we cannot reject the null hypothesis. So that means that our theory that plant height is controlled by monohybrid inheritance is supported. So we're now going to go through an exam question to see how sort of questions are laid out and what you may be asked. So a scientist investigated whether young or old blowfly larvae prefer light or dark conditions. In the first trial, the left side of a petri dish was covered to keep it dark and the right side was light. 5 blowfly larvae were added to each side of the petri dish, and after 5 minutes the number of larvae on each side was recorded. In the second trial, the same experiment was repeated, but with the right side dark and the left side light. The table shows the results of the trials. So that's a lot of information we've been given. So let's have a look at the table to begin with. So we have number of young blowfly larvae and number of old blowfly larvae, and then we have the left side and the right side. So remember that in the first trial, the left side is dark and the right side is light, and in the second trial, the left side is light and the right side is dark. And then we have the number of young blowfly larvae given for each side for each trial, which are young and which are old. So our first question is to give a null hypothesis for this investigation, and this is worth 1 mark. So if we work backwards here, if we were going to give a theory or a hypothesis, we could say that there is a significant preference of young or old blowfly larvae in choosing light or dark conditions. So therefore our null hypothesis is going to be that the larvae show no significant preference for light over the dark side or dark over light side. You can put either in. Question 2. The chi-squared test can be used to determine whether the results of this investigation indicate a significant difference in the distribution of young larvae between the light and dark side. So the key things you need to take for this question are young larvae and obviously chi-squared test, so we know that this is the test we're going to be used. So 2a, use the formula to calculate the chi-squared value for young larvae, and this is worth 3 marks. So we have our formula here. So our first step is calculating our expected values. We're not given any in this question, so we need to work it out ourselves. So remember that our null hypothesis states that larvae show no significant preference for light side over dark side or dark side over light side. So according to this, we would therefore expect the 5 larvae that are put on each side of the petri dish to remain on their side. So if you remember back to the information we're given, it states that there are 5 larvae put on each side of the petri dish in both trials. So therefore our expected values are going to be calculated like this. So we have our light side, so 5 from trial 1 plus 5 from trial 2 gives 10, and then our dark side, 5 larvae from trial 1 plus 5 from trial 2 gives 10 as well. So we would expect an equal division of larvae on both the light and dark sides according to our null hypothesis. So the calculation of these expected values will give you your first mark in this question. So we now need to record our observed values. So if we have a look at the table, I've just removed the old blowfly larva information just to make it clearer while we go through the question. So in the table it gives left side and right side, which can be a little bit confusing because remember we're focusing on the light side and the dark sides. So if we have a look at trial 1, our right side is the light side, so that gives 1 larvae. And then for trial 2, our left side is the light side, so that gives 2. So 1 plus 2 is 3, so that's going to be our observed value for our light side. We then have our dark side. So for trial 1, our left side, our dark side gives 9. And then for trial 2, our dark side is the right side, which gives 8. So 9 plus 8 is 17. So if we have a look at our calculations here, our light side, 1 plus 2 is 3, and our dark side, 9 plus 8 is 17. So remember, for the first step of finding our chi-square value using the equation, we then need to subtract our expected values from our observed. So our observed values for the light side was 3, remember 2 plus 1, 3. So that's going to be 3 take away 10, which is our expected value, which gives -7. And then our dark side, our observed value is 17. And then we need to subtract 10, which was our expected value, to give 7. So then next we need to square these values. So -7 squared is 49 and 7 squared is 49. So we then take our values of 49 and we divide them by our expected values of 10. So this is where we're going to get our second mark with the whole equation put together. So 49 divided by 10 is 4.9. So our chi-square values for both the light side and the dark side are 4.9. We then get our third mark by, of course, adding these together, so the sum of both sides. So 4.9 plus 4.9 is 9.8, so this is how we get our third mark. So part B of this question, the table below shows critical values of chi squared. Use your calculated value to determine whether the difference between the observed and expected results is significant. So in this table we have our probability value So this is probability value, and we have 0.15, 0.1, 0.05 and 0.025. So remember back to when I mentioned that biologists use 0.05 as our probability value, so we need to only be looking in this column here. So therefore 0.05 critical value is 3.84. So since our chi-square value of 9.8 is greater than 3.84, our critical value, this means the probability that the chi-squared value arising by chance alone is 0.05. So remember, biologists use this probability level. So therefore there is a significant difference between the observed and expected values. So the null hypothesis is rejected, and the theory that the young larvae share a preference for light or dark isn't supported. So this would be your overall answer for this question. So thank you all so much for watching. I hope you found this video useful and it's given you a better understanding of how to calculate and use chi-squared. Give this video a big thumbs up if you have found it useful and you did enjoy it, and make sure to subscribe down below so you don't miss out on any videos. Make sure to comment if you want me to do some more videos on statistical tests, and follow my social media to keep updated with my page and my videos, and I will see you in my next video. Bye guys.